and welcome to today's physics class. This class, we look at a topic called mirror formula. So let's look at mirror formula from start, and then we look at the several formulas for mirror. Then we have the concave mirror, convex mirror, and then we look at several important things to note in the study of mirror formula. First things first, note please. Couple examples. Note. The focal length of a spherical mirror, is related to its radius of curvature. I said the focal length of a spherical mirror is related to its radius of curvature by on the board please, F equal to R over 2. In other words, I can say that R is equal to 2F. Alright, so if you're having your focal length and the radius of curvature, these two are related by F equal to R over 2 or R equal to 2F. That takes me back to when I was solving problems under mirror. I saw a question there. It says give the mathematical relationship between focal length and radius of curvature. I saw that question. So it means that the relationship between focal length and radius of curvature becomes what there? This one there. That F is equal to R over 2 or F equal to 2 perhaps or R equal to 2F. This is the relationship between focal length and radius of curvature. Please note, please. Note, one line space paragraph, please. Note, when an object is replaced at a distance u, from a mirror of focal length f, and the image formed at a distance v, then they are related by, I said, when an object is replaced at a distance u from a mirror of focal length f and the image formed at a distance v, then they are related by, on the board please, they are related by 1 over f is equal to 1 over u plus 1 over v. This particular formula here is a formula for a concave mirror. Why? A concave mirror is usually positive here. Why a convex mirror, it will be what the negative. I will explain that as we proceed in the study of mirror formula. So I'm saying this please. In quotes, the relationship between focal length, image distance, and object distance. The relationship is what you have here, right? By the way, I said this one is for concave mirror, please. For concave mirror, right? So before I move on, let's define them there. What's F? F is focal length. Next up there, I have U. U is called the image distance. Sorry, object distance, please. Object distance, and V is called image distance. Image distance. All right. Of course, all these things here are in meters. They are all in meters. Right, so sorry, that's cm. It should be in cm, please. I'll give you why they are in cm. I'll show you why they are in cm. They are in centimeters, please. I will show you why they are in centimeters as we proceed. Centimeters. Usually, when it comes to mirror optics, right? If it from experience and from practice questions, practice questions, we do observe that all these things are given in CM mostly, right? So they don't usually in physics. Whenever you see CM, we convert to meter. But in these topics, optics, mirror, all these concepts here, we use CM the most, please. That's why I said you use CM, CM, and CM. I have this one on the board. At this junction, please note. If you are here, please note. Note the linear magnification in bracket capital M is given by the magnification in bracket capital M is given by, so now here the word linear magnification is M, and M is equal to V over U. That is, your V is for the image distance, your U is for the object distance. So magnification has to do with you first things first, place image before object. That's it. Anything that has to do with magnification is your ability to place image first before the object. That's the idea behind magnification. And I said this is its mathematical expression. By word, I have that magnification is equal to set V from here. You said V is what? Image distance. Of course, I have image distance. Alright, all over your U. Said U here is what? Object distance. I have object distance. This is your mathematical expression for magnification. Please don't forget the image comes before there, before object. Now, if you kind of try to ask me, what is the main definition of magnification? So put this down, please. Magnification is the ratio of the image distance. Copy that, please. Magnification is the ratio of the image distance to object distance, comma. It talks about how big or how small an object has been made. It talks about how big or how small an object has been made. Full stop, please. That is how you define linear magnification. So we have looked at relationship between focal length and radius. Done. We look at the relationship between focal length, image distance, and object distance. As you can see here, and I said this stuff here is an expression for what there a concave mirror. Haven't dealt with that. Look at linear magnification. It tells you how big or how small something is, and by expression it means image distance for what there over object distance as shown on the board. Please, this is this in this case, but in terms of height, please, in terms of height, what would be the expression for magnification? Please note that magnification in terms of height is equal to height of image over height of object. So HI means height of image over height of object. So here's the idea. Magnification, you will always have image first before object. So in full form, magnification in terms of height, I have height of object, height of image per se, image over height of object, height of object. All right, these are your other expression for magnification, as you can see on the board. So we have this stuff here for the idea behind magnification, please. All right, so at this junction, let's look at 12 important bulletins. My goal is this. I don't want to focus on giving you notes definitions. Let's get the key ideas behind these things and move on. Which way? So I have taken my time to draft out 12, is it 12 or 15? I don't know, but when we start, please. I have drafted out some key important things you need to know as a study mirror formula, right? So I'll give them to you one after the other. So let's look at another heading called Note the Following. Please, heading please. Note the following. Number one, an important heading. Please note the following, please. I'll give you, I think it's 15 or something like that. So let's just start this. Note the following, please. Note the following. All right. So note the following. Note the following, please. Number one, please. Number one. For a convex mirror, comma. For a convex mirror, comma. V is taken as negative in brackets minus. I said for a convex mirror, comma, V is taken as negative because a virtual image is formed behind the mirror, comma, focal length is also negative. Focal length is also negative. All right, so that's number one thing to note, that for a convex mirror, V is taken as negative. And I said why? Because a virtual image is formed. What's a virtual image? A virtual image is simply an image that cannot be caught on screen. I'll give you that later. Now what I'm saying is this. For a convex mirror, we said V should be negative. I have given you an expression for concave mirror. That's 1 over F equal to 1 over U plus 1 over V. That's concave. Now, for convex, we said that V should be negative. So let's say I'm having this place. So I'm saying this place. So number one, what we know before now is that we know that 1 over F is equal to 1 over U plus 1 over V. This man is for concave mirror. Now, when I said for convex mirror, that your expression becomes displaced. We said V is taken as negative. Why? Because a virtual image is formed. So I have that 1 over F for convex mirror is equal to 1 over U plus 1 over this V. We said takes V as negative for convex. We have minus V. In other words, plus times minus gives you a minus sign. So my expression for convex mirror becomes 1 over F is equal to 1 over U, minus 1 over V. This is your formula for a convex mirror. This one here is for concave mirror. Why this one here is for what there? For a convex mirror, as you can see on the board, right? And don't forget that we said U. This U is object distance, while V is image distance. Image U is object. V is image distance. U is object distance. V is image distance. Just try to know, like, differentiate them, please. I said U is object, while V is what the image distance as shown on the board. This is your first thing to know, that for a convex mirror you have this expression, for a concave mirror you have this one here. That's number one. Number two, please. Number two. So this is one I was trying to show you guys before. I was telling you that something is centimeter, other one millimeter. So I said this stops here. If you go and check past question properly, study past question most times, you will see that mirror formula, mirror optics concept there, they usually use cm for their unit. So put on this. Number two, for calculation involve optics. Listen, number two, please, and listen all what I'm saying on the screen. In case you can't get me properly or you mistakenly had me wrong, Everything is, I'll take my time to edit this video. So they're on the screen. So likely pause the video and write them down. You understand what I'm saying? So number 2, please. For calculation involving optics, the focal length, comma, object distance and the image distance are expressed in cm, centimeter. So as I'm saying earlier now, I said for calculation involving optics, the focal length, object distance and the image distance are expressed in centimeter. As simple as this. I never knew this before, right? It took me time, you know. Usually I do convert to centimeters, but I later observed that these things are always presented in cm. Why am I converting? So go and make your research and confirm what I'm saying. So don't forget that we said for calculation involving optics, so the focal length, object distance, and image distance are expressed in centimeter. That's about 2 bulletin to note as a study mirror. Number 3, please. Number 3. Number 3, please. Number 3. The nature of the image produced by a convex mirror, please don't forget, a convex has negative, concave has positive. So saying this, please. The nature of the image produced by a convex mirror, comma, irrespective of the position of the object, irrespective of the position of the object from the mirror, the nature of the image produced by a convex mirror, comma, irrespective of the position of the object from the mirror, is virtual erect and diminished. Is virtual erect and diminished. What do I mean? All right, so let's explain number 3. What do I mean by that expression? What do I mean? Okay, I said for a convex mirror, that convex mirror gives you a virtual erect and diminish, right? So for convex, so I'm saying that for convex, this creates a virtual erect and diminish. Where? Oh, okay. Erect, of course, and diminish. All right. So we said for a convex produces something called virtual and move on to erect and diminish. So I'll explain convex mirror properly now. Using 2 live examples. I'll use number 1. I'll use the shaving mirror to explain. Number 2, I'll use the mirror in the car. The one at the side of the car, right? So for number 1 there, let's try to explain convex mirror using a car. If you check a car properly, usually you have all been in a private car before, whichever one there. So if you check the mirror, the car mirror properly, you will see a description there. Yes, if you check a car, the mirror, let me just try to draw something out, something like this. So that car, the description here, there wrote something here. For those that do notice very well, what's written there? There's a particular word that is always written under that mirror. What do you think it is? So what do you think is written there? What will it be? Let me know in the comment section. What's written there? I want to get the answer to this, please. What is written? Literally, you're in a car, right? Some people just enter, they don't really observe a lot. So you should ask yourself, what's there? There is something written underneath that mirror. What do you say? Put on, please. So for those that don't know, please take note of this, please. Copy this down, please. Take notes. Objects on the mirror are closer than the seems or look. Objects on the mirror are closer than the seems or look. What does it mean? It means that, please guys, let's be neutral. In a real life sense, if I'm coming closer to you, see the way I'm coming closer to my camera, I'm getting bigger. If I go far, I'll look smaller. So on a normal sense, for an Homo sapien means human being. So for a human being, on a normal sense, when something is small, it means that thing is far. When something is closer to us, it means that thing is no longer far. It's something behind us, right? Now they are telling you that objects in the mirror are closer than they look or seems. So it means that, don't go and say because the car behind you is small, it is far. No, it is not far, it's behind you. Why it looks small is because it was designed with using what the convex idea. A convex helps you diminish something. Something is bigger, there's nothing bigger, it will diminish it. That's the concept. So if I have a camera this way, I can see like 5 cars that are behind me with my mirror. Why? Because my convex reduces, diminish everything to smaller thing there. So don't go and say that because my mirror, the car is small, it's small and I'm seeing it, so it is still far. Please, when you hit your brake, something can hit you behind. So there is this place. It is not far. The car is not far from you. It is because the convex mirror. That's why. So a convex mirror diminish something. So that's one scenario I can use to explain convex mirror for you. Number three is shaving mirror. Why shaving mirror? If you go to those old, I think in this century, we don't use shaving mirror again. What we go to barber salon that we do the cut there, right? We don't really use shaving mirror. But those that can relate will relate. Those that can relate will relate, right? So if you check back your shaving mirror, you have your mirror this way, and then you have the shaving stick this way. The reason why we call it shaving stick mirror is because that mirror was designed with a convex idea. Why? Because normally if I look at my mirror, it should be showing me like it be showing something literally the way I look. But convex will reduce my face. Like my face will look small in the mirror. If I do like this, I'll be able to see everything. Literally, it will diminish that your face, something smaller, and then you'll be seeing everything. Literally, all your faces in that mirror. They can just please. Some people cannot relate. Anyways, that's by the way, please. So that's like the idea behind a convex mirror. The idea there is this: it diminishes. It's virtual, erect, and diminished. So this is how I can try to explain the idea behind note number 3, which says the nature of image produced by the convex mirror is irrespective um, of the position of the object irrespective of what of irrespective of the position of the object from the mirror. You can see that. So irrespective of the position of the object to that mirror, it will diminishing it, it will take it down. So it is virtual erect and diminished. So this is like the idea behind note number 3. Number 4, please. Number 4, please. Number 4. Number 4. The magnification of a concave mirror. The magnification of a concave mirror. The magnification of a concave mirror can be lesser, equal to, or greater than unity. The magnification of a concave mirror can be lesser, equal to, or greater than unity. Why the magnification of a convex mirror? Why the mode there? Magnification of a convex mirror must be less than unity. Yeah. Now, please, you can hear the word unity, unity. If you are familiar with science term very well, unity in science term means one. So we are saying this for a concave mirror. For a concave mirror, the magnification, the M for a concave mirror can be either less than 1, greater than 1. I said can be what there can be lesser, equal to, or greater than 1. That's unity, greater than unity. So this one can be less than 1, equal to 1, or greater than 1. That's for concave. For convex, please, it must be less than unity. It must be less than 1. Hi, yeah, yeah, yeah. For listen, please, guys. Concave must be either lesser, equal to, or greater than 1, while convex must be less than 1. How can we apply this? So we said, please, the multiplication of these two for this one there, it must be less than 1, and that's true. If I have my camera here, let me show something, please. I don't think you can see what I'm doing, right? So this is my camera here. You can see my camera. You see, we have some what's it called? I'm coming. I have some number here. You can see. See the way if I increase my zoom in, you can see. So we said for a convex mirror, that stuff must be less than 1. It means if my zoom in is less than 1, it is 0 point, it should become, if I show my face, my face looks smaller, right? So look at it, guys. I don't know how to explain this. You guys get it very well. Okay, let me just try to explain using some ideas, please. You know, on your camera, you have some readings like your zooming. This one, then like literally when you are zooming your camera, you see those numbers written 0.2. So yes, please. So the more I go backward to 0 point, no matter how I move less than 1, I then go beyond 1, I move less than 1, your camera will be going backward. But if I zoom it from 1 and upward, the camera comes closer to me, literally. So for a convex, we are expected to put zoom in the camera backward from 1 backward. So it was less than 1, and if it's less than 1 there, it means that your face will look smaller. You capture literally everything. But when you zoom it fully, for as concave, because concave can be lesser, concave can still be equal to 1, concave can still be more than 1. So whichever one there, if I zoom it up fully, you know, it will show my face. Literally, it can even show only my nose. My face and my nose, you know, because I have zoomed that stuff so much that it could only just see my face. That's for concave, please. For convex, please note that is what less than 1. That's what I want you guys to note as we proceed in our study of mirror formula, please. All right, so let's proceed, please. Where were we? Where are we? Okay, that's number 4. Number 5, please. Number 5.